Have you ever wondered how your GPS just knows the fastest route? Like it's magically dodging traffic, you can't even see it? Or how a character in a video game seems to hunt you down with terrifying precision? Well, it all boils down to a fundamental concept in AI, search. Today, we're going to pull back the curtain and see exactly how an AI finds the smartest path from point A to point B. I mean, really stop and think about it for a second. In less than a blink of an eye, your phone considers this insane web of possible roads, intersections, and traffic flows to find that one single optimal path. It's a gigantic puzzle, right? A classic search problem. And it's something AI is incredibly good at solving. So to really get our heads around this, we're going to use a super simple analogy for this whole explainer, an AI agent trying to solve a maze. And just remember, this maze isn't just a maze. It could be a map for your GPS, a game board, or pretty much any problem with a start and a finish. Okay, so let's meet our little puzzle solver. In the AI world, we call this an agent. It's a fancy word for a simple idea. It's the thing that's actually doing stuff. For your GPS, the agent is the car. In our maze, it's our hero, the one trying to find the way out. Now, our agent can't just start running around blindly. Before it makes a single move, it needs a rule book. It has to understand the world it's in, what it's allowed to do, and what the final goal is. This setup phase is absolutely critical for any AI search problem. First things first, the agent needs to know its state. A state is really just a snapshot in time. For our little maze runner, a state is simply the exact square it's standing on right now. Every single square in the maze is its own unique state. And from any given state, any square, our agent has a list of possible actions. These are its choices. In our maze, it's super straightforward. It can try to move up, down, left, or right, as long as there's not a wall in the way, of course. Okay, so what happens when the agent actually takes an action? That's where something called the transition model comes in. You can think of it as the physics engine of the AI's world. It's a simple rule that says, hey, if you're in this state and you take this action, you will end up in that new state. It's just cause and effect. And last but not least, how does our little agent know when it's won? It uses a goal test. This is a super simple question it asks itself every time it enters a new state. Is this it? Am I at the finish line? For our agent, it's literally just checking, is this the square I was looking for? And this right here is the key. Before an AI can even think about searching, the entire problem has to be defined by these four things. Where do I start? What can I do? What happens when I do it? And how do I know when I'm done? Once the AI has this complete rulebook, and only then can it finally start hunting for a solution. All right, setup is complete. Our agent is ready to go. So what's its first move? We're going to start with a simple kind of brute force approach. It's called breadth first search, or BFS for short. Look, it's not the most sophisticated strategy, but you got to admit, it is incredibly thorough. I want you to imagine dropping a pebble in a pond. BFS works just like those ripples spreading out. It starts at the beginning, and it checks every single square that's one step away. Then it checks all the squares that are 2 steps away, then 3, and so on, expanding outward in a perfect circle. The big win here? Because it explores level by level, it is guaranteed to find the shortest possible path. The downside, yeah, there's a downside. It explores a ton of useless squares to get there. So how does it pull off this perfect wave-like search? It uses a neat little data structure called a queue. The best way to think of a queue is just a line at the bank. First one in is the first one out. For our agent, this means the very first options it finds are the very first ones it explores. And that's what forces it to expand one level at a time. And hey, for all you coders out there, this is what that logic looks like in Python. Don't get lost in the details. Just look at this one line right here. Node equals self.frontier 0. See that little 0? That's just telling the computer, hey, grab the very first thing on the to-do list. That one simple command is the entire secret sauce behind how breadth first search does its thing. Okay, so BFS works. It's reliable, but it's also uninformed. It's searching totally blind with no sense of direction. What if we could give our agent a little bit of intelligence? Like a sixth sense to point it towards the goal. Well, this is where the amazing idea of a heuristic comes in. So what is a heuristic? Honestly, it's just a fancy word for an educated guess. It's a rule of thumb that helps the AI estimate how close it is to the finish line. It doesn't have to be perfect, not at all, but it gives the agent a much-needed sense of direction.
It's the difference between wandering around in a dark forest and having a compass. And for a problem like our maze, one of the best heuristics is called the Manhattan distance. It sounds complicated, but it's brilliantly simple. You just count how many squares you'd have to move left or right, and how many you'd have to move up or down to get to the goal. You just completely ignore the walls. It's an optimistic guess, for sure, but it does an amazing job of pulling the search in the right direction.
So what happens when you take the systematic, thorough approach of our brute force search and you combine it with the intelligent sixth sense of a heuristic? Well, you get one of the most famous, most powerful, and most widely used search algorithms of all time, A-star search. We say it A-star.
The absolute genius of A-star is how it makes decisions. For any possible path, it's always balancing two things. First, it looks at G of n. That's the actual cost, the number of steps it's already taken to get here. Then it adds H of n, our heuristic, that educated guess of how much farther it thinks it has to go. It always explores the path with the lowest total score, which makes it incredibly smart. And this really gets to the core of it all. BFS, our uninformed search, is like driving while only looking in your rearview mirror. It just expands blindly based on where it's been. But A-star, our informed search, looks at the rearview mirror and looks ahead through the windshield, using its heuristic as a guide. It searches with a purpose, and as you're about to see, that makes all the difference. So how much of a difference are we talking about? Well, it's pretty staggering. In our maze, the blind, uninformed search had to explore 399 different squares before it finally found the solution. But our new, smart A-star search, using its heuristic sixth sense to guide it, it found the exact same perfect path by exploring only 77 squares. That is over 5 times more efficient. This isn't just about being faster, it's about being fundamentally smarter. And this is the main takeaway from all of this. The secret to powerful AI search isn't just about throwing more computer power at a problem. It's about being clever. It's about using problem-specific knowledge, a good heuristic, to make smart guesses and to avoid wasting time going down dead ends. So let's just quickly recap. AI solves problems by searching through a state space. Uninformed searches like BFS get the job done, but they can be super slow. The game changer is the heuristic, that educated guess that makes the whole process smarter. And that's what lets informed searches like A-star find the best solutions so efficiently. And that leaves us with one last big question to think about. We just saw how a really simple, educated guess, the Manhattan distance, made our maze solver dramatically better. So when you think about the incredibly complex AI all around us, the one that recommends your next movie, or translates languages on the fly, or even drives a car, what are the really clever, invisible, educated guesses that are guiding them?